You can actually use Q&A board to write your question during the presentation or after the presentation, whenever. And later, all the presentation is finished, the panelists and organizers and presenters will answer those Q&A questions. And also, if you want, you can actually speak up and you can give a mic to you so that you can actually ask questions directly. Okay, so then let's get started.
Okay. Hello everyone, this is BiS987 Biofusion Seminar. This is Group 3. Today's topic is neural interface, bridging humans and machines. Moderator Kyung-Lim Lee will progress the seminar.
Hello, I'm a moderator Kyung-Lim Lee. This webinar consists of presentation, discussion, and Q&A session. In the presentation session, Keum-Seok Nam and Keun Chang-Sung will introduce about neural interface and signal analysis. And in the discussion session, 3 panelists, Si-Won Moon, Dong-Hyul Seok, Min-Gi Kim, will discuss about ethical problems, utilization, and applications of neural interface. First, presenter Keum-Seok Nam will start the presentation about neural interface.
Okay. Hello, my name is Keum-Seok Nam. I am a first-year master's student at Professor Sung-Joon Park's lab, and I'm working on neural interfaces in a variety of formats, such as fibers, e-skin, and rehabilitation interfaces. Welcome to our Biofusion seminar on neural interfaces, bridging humans and machines. Today, we will give you a brief overview of what neural interfaces are and highlight recent advancements in this field. To begin with, what are neural interfaces? There are many ways to describe neural interfaces, as it is such a broad term. A recent paper in Nature Electronics described a neural interface as a bidirectional communication channel between a subject's nervous system and a man-made device. Simply put, neural interfaces act as bridges between humans and machines. But how do they do so? The main modality used thus far is electrical. Electrical recording has been used to observe neuron activity in the form of local field potentials, and if possible, single unit activity. As neural interfaces provide bidirectional communication, neural activity has also been modulated with electrical stimulation. Furthermore, alternative modalities with chemical sensing, drug delivery, and optical control with optogenetics are also emerging. Today, we will focus on the electrical interfacing of neural interfaces. However, we would like to mention that there are many emerging modalities, such as ultrasound, chemical, and magnetic, that we will not discuss today. A recent example of electrical interfacing with the brain is Neuralink. Many of you in the audience may have heard of their recent demonstration, where they exhibited their neural interface trial on pigs. You can see the device on the bottom left. It's a circular device with thread-like extensions. These thread-like extensions are implanted into the brain, as shown on the top left image. Each of the black threads in the photo are one of the threads attached to Neuralink, and each thread has multiple electrodes to get a total of 1,024 signals from various locations in the brain with a device the size of your finger. So what can it do? Besides controlling computers with just your brain, the Neuralink team has shown application to predict gait analysis through the recorded brain activity, suggesting use in rehabilitation and prosthetics. To get a better sense of what's exactly happening, let's look at this video here. So this video, you can see the black threads being inserted into the neural tissue. And then, although it looks quite big in the photo, these threads are on the scale of hundreds of micrometers, so they're very, very small, requiring very precise work. To illustrate the gait analysis, here, the Neuralink team showed the applications for the Neuralink. So you see 4 different signals, and each signal is like a different point on the pig's leg. So the thick line is the actual motion of the pig, while the faint line is the predicted gait motion from the Neuralink signal activity. So this suggests that Neuralink can also be used for rehabilitation. Although animal testing is still being conducted by Neuralink, it is exciting to see how soon this technology can soon be applied on humans. Another example that I would like to highlight is in rehabilitation. Not only can neural interfaces read brain activity, but they can also be used to modulate our body. In 2018, the Corteen group at EPFL demonstrated restoration of walking in patients with spinal cord injury. These patients had not been able to walk or were severely impaired for over 4 years. During the study, an electrical stimulation device was implanted into the lumbosacral spinal cord, and rehabilitation sessions were conducted with stimulation occurring during the intended movement. After a few months of rehabilitation, the participants were able to walk voluntarily without stimulation. I hope these examples of neural interfaces have demonstrated their potential applications. As you have just seen, there are many applications of neural interface, and with each application, the form of the device changes. Today, we will largely introduce 3 types of devices. I will introduce invasive probes, and the next presenter will introduce semi-invasive devices, specifically electrocorticography, or ECOG, and non-invasive devices such as EEGs for signal analysis. The simplest way to differentiate these devices is in the physical location of the device. Invasive probes are directly inserted into the neural tissue. In contrast, ECOG devices are placed on top of the cortex, but they require surgery, which is why this is termed semi-invasive. EEG devices are placed directly on the scalp, but don't require surgery. Due to the different physical locations, there are limitations in the neural activity that can be obtained in each interface. Invasive probes are able to measure the activity of single neurons and gather much more information, while EEGs are only able to obtain the combined activity over large areas of the brain. However, invasive probes are currently limited in use as they destroy neural tissue when implanted. The common types of invasive probes in the 20th century are the following. Initially, neural probes were made of metal wires. These metal wires were twisted in pairs or fours to create stereotrodes and tetrodes respectively. However, with the development of IC technology, multi-electrode arrays on silicon substrates have been widely developed. Specifically, 2 main architectures are prevalent: the Michigan probe and the Utah array. The Michigan probe is a single line or shank, and many electrodes are placed along this shank. This allows signals to be measured from multiple depths. However, there is no longitudinal resolution for the Michigan probe. In contrast, the Utah array only has electrodes at the tip of each support. Thus, it can measure activity from wide brain regions, but not depth-wise. The neural pixel is an example of a recent Michigan probe. The device was published in a Nature paper in 2017. You can observe that it has a Michigan probe architecture with 1 shank, but many electrodes with significant improvements in contrast to the previous slide. The neural pixel has 960 recording sites and are able to measure brain activity from 5 regions in the brain simultaneously. In addition, these devices are very small. This device is 70 microns wide, which is about the size of your hair, to put it in perspective. And this size is necessary in order to minimize tissue damage during insertion. Although the performance of these devices is impressive, rather than increasing the electrode number, many efforts have also shifted to creating softer neural probes. A major obstacle in use of the invasive probes shown previously are in chronic use. When used in humans, these devices must be used for decades, and each time the device is replaced, it would create additional brain damage and additional surgery. Specifically, the stiffness of silicon is on the scale of gigapascals, while the stiffness of tissue is that of kilopascals, which is a 6 orders of magnitude difference. This creates a mechanical mismatch between the device and the tissue during micromotions of the body. This causes cell death near the surface of the device, and the cell death prevents interfacing between the device and neural tissue by creating a functional encapsulating layer. So this functional encapsulating layer kind of acts as an insulation layer, which prevents the signal from being modulated and signals from neural activity from being read in the devices that are produced. To address this obstacle, there have largely been 2 approaches. The first approach is to change the shape of the device. Instead of making it a stiff shank, the electrodes are produced in a mesh shape, which allows deformation in the brain by making the device flexible. The second approach is to change the material. Recently, devices with reduced mechanical modulus have been widely used, such as PDMS, with organic electrodes such as PDOC-PSS through 3D printing. So these organic materials have a mechanical modulus on the scale of megapascals, and some are even of kilopascals. In addition to making softer neural interfaces, additional functionalities have also been added. Chemical and optical capabilities have also been developed to supplement electrical interfacing. Specifically, many devices have been produced for optogenetics, as chemicals are required for the viral modification and light is needed to stimulate cell-specific activity. In addition to common silicon fabrication processes such as lithography, neural fibers have also been developed with the thermal drawing process. Neural fibers enable a mass-producible method for production with easily integratable multifunctionality. A large preform with desired components are created and thermally drawn to create devices that are hundreds of micrometers wide, in contrast to silicon processes, which have stringent and lengthy development procedures. Multifunctional neural probes allow a variety of soft materials, such as polymers and hydrogels, to be used for probes with mass-producible, multifunctional, and soft neural probes. I hope my presentation has given you a brief overview of neural interfaces and invasive neural probes. Thank you for your attention.
Thank you for your presentation. Next, second presenter, Keun Chang-sung, will introduce about signal analysis.
Hello, can you hear me? Hello?
Yes, I can hear you.
Does the screen is okay?
Okay.
Okay. Hello, I'm Keun Chang-sung, the second presenter of today's topic, and studying on biosensor chip under Professor Chul Kim. At the first session, we briefly look around why neural interface is so popular these days and electrodes, the base technology for neural interface. Now I'll guide you on what signals we are collecting for neural interface and how to interpret it and writing rather than reading. So the different organs of our body, such as our brain, arms, leg, and heart are is read through electrodes. The brain, in particular, is a collection of numerous neurons that serve as a commander tower to collect, integrate, and analyze signals from different locations and command how they react. So many neural interfaces are targeting brain signal. In order to interpret the signal, it's necessary to convert them into computer readable data. The brain signal read from electrodes are typically several dozen of microvolts, which are too small for computer to read directly. Our most common battery is only 1.5 volts, so compared to the battery, the brain signal is only 1/1,000,000 times smaller than that. So we use the amplifier to amplify the signal size, and then we use it in the digital signal that computer can read using this analog to digital converter. Then our computer or some sort of digital processor interpret it according to the pre-programmed algorithm. Then we can manipulate the device using that analyzed outcome. And here I briefly remind you about the signals. It is important to get good signals that are big and noiseless signals using smaller. Signals usually get smaller as they get farther away from the signal source. So the farther away electrodes are from the signal source, like brain or nervous, the source smaller the signal they lead. And since signals from different regions are merged together in distant place, it's difficult to distinguish specific information. So in previous session's video, neural links open the head and put electrodes directly into the brain to get as big and clear signal as possible. For brain signals, we differentiate the names of signals by the distance between the electrode and the brain, from the inside to the outside except this penetrating one. It is called the ECOG and EEG. ECOG puts electrodes directly on the brain cortex without penetrating them, so it's less likely to damage the brain than to stick it. Since it's very close to the brain, you can get a good signal, but this also requires surgery because you have to open the skull. EEG puts electrodes on our scalp, so the electrodes are relatively far from the brain. Signals are small and noisy, but they are very safe because they don't require surgery. Okay, then next, let's move on to the next one. After you watched all this stuff, you will naturally ask question, okay, this is easy signal and it looks very noisy. How can we read information from it? ECG or action potential has its own characteristic waveform and characteristic moment, so we can convert it into numbers. But the brain signal itself just looks like a simple noise like this. So we can't do anything with this step. In order to do something, we need to find the characteristic of this signal and change it into numbers. If there are numbers, you can calculate and statistics and create formulas and so on. So scientists have created lots of ways of extracting and analyzing signals characteristics in numbers. Those methods include FFT, independent component analysis, ARM, LT, LDA, SVM, AN, and KN, and so on. So there are so many ways. Since there are so many kinds of it, it takes too long to explain one by one. So I won't go detail in here. So just explain as a whole briefly. If I describe this method simply as a whole, it can be called a set of words that divide signals into different basic signals, make data from numbers representing the time, voltage, frequency, etc. of that signal, analyze those data in statistical way or in machine learning methods to classify what information each signal is present. By developing a way to turn signals into information, our devices have finally learned how to connect our bodies with our machine. Scientists are not only reading information like this, but also trying to enter information by stimulation, that is, writing. The deep brain stimulation looks similar to what the first speaker showed us, could be one example. If you put electrode deep in the brain, and if you give stimulation, the symptoms such as severe tremor, the handshaking, are alleviated. And there is another technology called cochlear implant. It's a device that gives hearing back to hearing impaired people. The system works as follows: receive external sound like a mic and convert it into frequency and amplitude information and give electrical stimulation to the auditory nerve in the ear. There are neurons in our ears that react only to specific frequency. So by artificially stimulating these cells, the hearing is recovered. But these technologies still have a lot of problems to solve, especially technology like DBS to stimulate, and our body is a very good conductor. It's like painting with a marker on damp piece of paper. To give you the exact information, you need to dot only this small area here, but as the marker is pressed, the large circle is drawn. So scientists are trying to make a thinner pencil or looking for other writing instruments like ultrasound wave or light or anything other than electricity. Like this, there are still many obstacles to complete communication between brain and the computer, but many scientists are still working on it because if they realize they can make many dreams as a real. Thank you for listening. And here is the references I used. Thank you.
Thank you for your presentation. Now we will have 3 panel discussions. First, panelist Siwon Moon will discuss about ethical problems.
I'm the first panelist, Seo Moon, and currently working on organoid under Professor Pilnam Kim. And today I'm going to talk about possible ethical issues of Neuralink. Elon Musk announced that one of his companies, Neuralink, had implanted an interface about the size of coin into the skull of a pig named Gertrude. Neuralink researchers wirelessly linked the brain to an external computer to establish a connection between the two. Whilst the device is not yet approved for implantation into a human brain, the company also announced that it had obtained U.S. Food and Drug Administration approval to expedite the regulatory process toward this goal. This brain-computer interfacing technology might be thought of as another step on the road to a merger between humans and artificial intelligence. It could enable a human to control a cursor, wheelchair, or drone by mental act, rather than a more conventional bodily action like pressing a button or controlling a mouse by hand. But there are more complex potential consequences to consider. The first thing to consider is privacy. There are gaps in legislation regulation of BCI data. BCI data, which can potentially contain elements and indications of one's memory, personal preference, and emotional inclination, should be tightly regulated. Musk's company is registered as a medical research company for now, but Elon Musk has stated the ambition of creating potential non-medical applications of enhancing able-bodied humans. There are standard guidelines and regulations in place for BCI clinical trials, but there is currently no legislation for its non-medical research application. Legislators should regulate how the BCI-related neurodata is stored and used to protect consumers' neuroprivacy. The next is coercion. Elon Musk argued that for people to be productive in a future society, they will have to incorporate a BCI. This leads to the issue of coercion. Take a famous cyborg, Todd Turner, as an example. He has been carrying his machine extension, the precursor to Google Glass, since 1993. On NPR, he shared his experiences with Lizzie, his extension. He mentioned that he had Lizzie with him during his PhD or qualifying exam and was able to look up detailed information online using the computer. If this type of technology becomes prevalent, as Musk projects it to become, the standard of performance will be raised. People will have to start wearing their own BCI to match others' performance. The technology will change the perceived normal function and capacities of humans. This can create implicit coercion if people using BCI gain an unfair advantage and others are forced to start using it to not fall behind. Another point to be considered is personhood. According to Starner in the NPR interview, he claimed to be better with people when carrying Lizzie. However, the interview did not feature perspectives from friends and colleagues of Starner. How BCI can alter self-perception needs to be examined. Is the BCI an extension of the user or is it merely a tool? How does it influence or interact with the user's personality? To what extent is the user responsible for the decisions made by the interface? For example, who is to blame if a person commits a crime under the influence of the interface she is carrying? Companies such as Musk's Neuralink, along with legislators, need to address these questions when developing brain-computer interfaces. Each electronic gadget available today, from desktop to cell phones, needs to go through a guideline procedure with different government organizations to guarantee it is protected to use before it tends to be offered to the overall population. A similar will be valid for the Neuralink brain chip, and in certainty, the administrative checks are relied upon to be more top to bottom than for a customary gadget. Due to the fact that a Neuralink establishment will require a type of medical procedure, Musk's task will require endorsement from the US FDA before it can start preliminaries of the inserts. Just in the case that medical specialists see any hazard with the automated period of the medical procedure, at that point, it could put the whole task on hold. Likewise, governments around the world will probably need to run free examinations to decide the effect of having a remote sign transmitted to and from an individual's mind. Some portion of the examination will destroy in cybersecurity specialists to check the potential defects in the Neuralink programming structure. So here ends my presentation about possible issues of Neuralink. Thank you for your attention.
Thank you for your discussion. Second, panelist Dong-Yeol Seok will discuss about utilization of neural interface.
Can you hear me? Okay. Hello everyone. I'm Dong-Yeol Seok and
잠깐만. 지금 화면이 지금 바꿔야 될 것 같아요. 디스플레이 설정을 바꾸세요.
프레젠터보다 있군요. Now is it okay?
It's okay.
Thank you very much. Hello everyone, I'm Dong-Yeol Seok, a master course student studying in bioelectronics lab of Professor Chul Kim. I'm working on developing motion artifact-free EEG electrodes. In this session, we're going to think about whether neural interface devices will be used in real life in the future. For someone who have really optimistic views about the future, it may not even sound like a question. However, for the advance and the application of technology in the real life, there are many conditions to be prepared. We're going to talk about the conditions with a case of neural interface technology. Okay. Before we discuss the conditions, I would like to clarify the view of the future we are talking about. In a future where neural interface devices are used in real life, implantable neural interface devices are reliable and available solutions for patients suffered from neural diseases. As you may already know, many neural interface devices in development now aims at treating neural diseases or supporting lost functions of nervous system. Neural prosthesis can be a good example. In the future, People will be able to overcome the neural diseases or trauma by utilizing neural interface devices. On the other hand, there are expectations that neural interface technology will provide more convenience, efficiency, or even joy to our life. Controlling machines without moving hands only by thoughts, communications with neural interface devices. You might once have seen those devices in SF novels or movies. Those devices are not for medical purpose, but for ordinary purpose, where those features will be brought someday. In order to think about the feasibility of those features, we have to answer those three questions. First, it is about the usefulness of the technology. Are neural interface devices useful enough for patients or other customers? This is an important question because it is the fundamental motivation for the advance of the technology. Second, we have to know about the technical requirements for the reliable use. For the view of feasibility, it is the most important question because we need proper functions of devices and also the safety and reliability. For the third, we have to discuss whether those technical requirements can be fulfilled by current or future technology. Okay, first, I would like to argue the usefulness of neural interface devices. I think the answer for this question, are neural interface devices useful enough to patients or other customers, is undoubtedly yes. You may heard about the cochlear implant. It is one of the neural prostheses that converts sounds to electrical signal and send them to the sensory nerve terminal in the cochlea. It helped 600,000 of people who had hearing impairments in the world. Deep brain stimulation became a treatment for drug-insensitive cases of Parkinson's diseases. Since the diseases or trauma or nervous system can be directly related to the quality of life of patients, the application of neural interface devices as medical treatment will be uncountably valuable. The researchers about neuroprosthesis are going on now, and if it can be used in real life, it will help maximum 2% of people in the world who are suffered from paralysis or loss of limb functions by other trauma. For the other supportive reason for claiming the usefulness of neural interface devices, desire for convenience and efficiency will never vanish. As we have seen in a future where neural interface devices are used for ordinary purposes, it will help people controlling machines conveniently and help communicating quicker. It may not sound appealing enough to make people research and develop neural interface devices for those purposes. However, if those technologies are available, the transition of the realm of application can be really quick. So I think neural interface devices will be undoubtedly useful. Then if it is made, how should neural interface device be like? Since devices in real life should be remained robust and safe in various conditions we face in the real life, there are lots of technical requirements compared to the devices tested in the laboratory. As the real application of implantable brain-machine interface devices becomes an issue in the medical device markets, FDA issued a draft of regulation guidelines for implanted brain-machine interface devices. It shows some aspects of technical requirements. First of all, the performance, biocompatibility, long-term safety issue must be the most important requirements. Those devices should be able to require reliable neural signals at the regions of interest for a long time without making any safety issue. Moreover, there are many circumstances that devices might face in the daily life use. It can be exposed to electromagnetic interference. For this reason, electromagnetic compatibility and MR compatibility are one of those things to be considered. Also, the products must be sterilized while they are being distributed and stored. The use of medical devices is approved when the requirements are fulfilled so that the benefit of the device overwhelms the risk of the use. For now, FDA considers implanted neural interface devices only as medical devices. It it implies that the neural interface devices of medical purposes are expected to be used in real life in a close future. Then can technology satisfy the technical requirements someday? I would like to say it is approaching. You may have seen the good products in the clinical tests introduced by the former presenters compared to the interfaces introduced 10 or 20 years ago. Many products now can acquire signals from more channels with more biocompatible methods. There are many products being tested with the approval of clinical tests by FDA. Neuralink is one of the good examples. The long-term safety issues are also being considered during their development process because companies aim at launching them in market. Moreover, the researches of neuroscience will be accelerated as the neural interface devices becomes more available and reliable, since they will have more opportunities to observe neural phenomena with better resolutions and accuracy. The knowledge obtained from the research will fertilize the environment for the application of neural interface devices for medical or ordinary purposes. It makes me have positive expectation about the future of this technology. Then, what will be the proper conclusion about the feasibility issue of neural interface devices in real life? I would like to summarize like this. Neural interface devices are undoubtedly useful when considering the medical application of this technology. Also, it has a big potential of use of ordinary purposes as well. Although there are many requirements related to the reliable performance and safety issues, the standards for the regulation is being made for the medical use of neural interface devices, and the front line of technical advances approaching to the regulatory standards. So it is reasonable to have positive expectations to see neural interface devices for medical purposes in a closer future. Also, the development of devices itself will accelerate the researchers for the applications as well. Okay, what do you think? These are my references, and thank you for listening.
Thank you for your discussion. Lastly, panelist Mindy Kim will discuss about application of neural interface.
Hey, good afternoon. I am third panelist of our group and I study biosensor under Professor Yongho Cho. Here I will simply talk about the future of the neural interface. So far, we have explored neural interfaces by looking at the definition of neural interfaces, what they are, commercialization possibilities, and moral issues. This time, I will briefly introduce the problems and requirements to see what improvements may appear in the future. Starting with accuracy improvements. Since the brain's action takes place through a very complex process, research that clarifies the certain algorithm between the reactions is needed. To analyze brain activity, as we talked already, the brain-computer interface recognizes brainwave stimuli, pre-processes it, performs feature extraction, and orders input-output devices after the classification process is performed. It is natural that errors occur because there are several processes, but high accuracy is required to be widely used. Fortunately, most of studies so far have high accuracy, around 80 accurate, but there is still a need for improvement. So those accuracy improvements will appear in the future, maybe by mixing it with multiple interface technologies, such as motion sensors at head and limb movements, vital signs using heart rate, and visual movements of eyes, or maybe predictive correction using images by deep learning. Next, the safety improvements. There are two main methods for measuring EEG, invasive and non-invasive methods. Invasive methods measures EEG by applying a microchip to the scalp, while non-invasive methods measures by helmet or headset type equipment. Safety is important for both methods, but in the case of an invasive method, the chip is planted directly to the brain. This needs to be more concerned about safety. Among the devices using the invasive method, Neuralink, which is the most popular, has a dedicated surgical machine for implantation, but only 87.1% success rate was achieved as a result of animal experiments. Therefore, improvements in safety will appear in the future, maybe by structural improvements through MEMS technology, or maybe by human clinical study. Lastly, the diversity improvements. Just as various BCI or BMI studies, such as moving a robotic arm or controlling a drone with brain waves, have been conducted so far, more diverse and novel studies will be conducted in the future. For example, artificial muscles for the treatment of chronic degenerative brain diseases, treatment of mental brain diseases, transfer of emotions to robots, transportation or smart home using BCI may appear in the future. In the past, the word interface was used limitedly in computers and was represented only by keyboards and mouse. However, with the advent of various digital devices such as smartphone or VR in recent years, the scope of application and information input-output methods are diversifying, and the importance of the user interface is greatly highlighted. BCI has emerged as an alternative to meet these demands for next-generation interfaces, and in particular, it continues to develop with the promotion of brainwave research and the expansion of the use of BCI technology. It is expected that the BCI interface will eventually evolve to BBI, which means brain-brain interface, through CBI, which means computer-brain interface. In the distant future, it will be possible to control animals or robots by inputting brainwaves into computers. Not only that, the era of wireless communication, which uses brain chips to transfer thoughts between people from brain to brain, may also begin. Here are the references, and this is the end of my presentation. Thank you for listening.
Okay, thank you for all the presenters and panelists. This is all of our presentation and panel discussion. If you have any questions, feel free to ask us. Thank you.
So you can use a Q&A board, or maybe you can actually, if you want, you can actually open mic for you, so you can actually answer question directly.
There is a question from Anna. The question is that, are there any recorded side effects of using PCI apart from the privacy and safety issues? Is there anyone who can answer this question?
Actually, I didn't find about any side effects of BCI, but about Neuralink, I guess we don't know about side effects yet because implantation into human brain is not yet approved. So, but I don't know in detail.
Thank you for the answering. This was an answer from Siwon Moon. Is there another question? There is a question from Hamza. A question that, in your opinion, how can legislation be done to address ethical issues related to brain-computer interface?
Well, I would like to answer this question. Maybe we might have a more legislation about the regulation related to the technical issues, so it can secure the privacy or about how they should handle the information from the people's body. Or we may have criminal laws related to the crimes that might related to the BCI machines as well.
Thank you. It was answered from Dong-yeol Seok. And there is another question. The question is, what is the new thing in Neuralink compared to other neural interface devices?
To answer this question, what was really great about Neuralink compared to other neural interface devices is that was kind of the scale and the system capabilities of the device. In research, many of the devices usually have limited number of electrodes. For example, in soft neural interfaces, there's around 10. And in the silicon-based neural interfaces that I introduced, such as NeuralPixel, there's 960. Only in one spatial vertical location. But Neuralink had like a large spatial resolution. So it covered a large area with lots of electrodes. And it further demonstrated how the signals can be used. So they showed that they can be used to predict gait analysis. And furthermore, the recent demonstration that they showed, it was, I think, very big that they showed their use on pigs, because whenever you change the animal model, there's a lot of unique challenges that must be addressed.
Thank you for the answering. It was from Kim-seok Nam. There is a new question from Jong-sol Kim. The question is that neural electrodes seems like very sensitive. If someone has a chip on the brain, can electromagnetic waves from devices such as computers or phones affect them?
Well, I'll answer that question. The chip, yes, also records the other electrical signals from the surround and also the other parts of brain that we are not interested in. So we should use some kinds of filters or digital process algorithm to remove those unwanted signals. And we have to precisely calculate how much those noise are coming into the device, because some noises like common mode interference are much higher voltage than the neural signals, so it may saturate the amplifiers or devices, so it will become a lot of obstacle to build such devices.
Thank you for the answering. The answer was from Kun Chang-sung. Is there more question? If there's no more question, we're gonna wrap up the seminar.
Okay, thank you much for excellent organization. I think it's time's up. Okay, and so great. So then we can continue this this biofeedback seminar in this way in the next time as well. Okay, thank you much and have a great Thanksgiving break. Thank you and see you later. Bye.
Thank you.